Welcome to the 12th session on measure theory. At the end of the last session, I said we will start on measurable functions. I'm sorry, I'm not going to do that. I want to introduce the notion of abstract measurable space and measure. This is very important, and because later on, usually whenever I teach first course in measure theory, I follow exactly what I was doing so far, and I also introduce abstract measure theory because you will see, as I said in the beginning of the first three lectures on motivation lectures, many of the things integration theory can be set in a very abstract setting. The moment I have a set X and a class of subsets on which I can define what is called a measure, okay, I can do integration. Okay, this is what I more or less said. I do not know how many of you followed. That doesn't matter. Okay, it's some kind of a tip of an iceberg, okay, to say what's happening. So we are going to introduce, you will see the benefit of learning this, okay, soon. Okay, so let us get started. Yeah, so let X be any set, okay, and B class of subsets of X. Then I say B is a sigma algebra. Sigma algebra if it satisfies the following three conditions. Empty set belong to B, and 2, whenever E belong to B implies E complement also belong to B, and 3, whenever I have a countable collection En belong to B for all n implies union En belongs to B. That's it. Sigma is for countable union. Do you remember F sigma set? That is countable union of closed sets. So okay, sigma stands for S. S is sum, which is union here. Okay, so that is why it's a sigma algebra, and this is the thing. This definition is extremely easy. There is nothing. Notice that 1 and 2 implies X also must be there, right? So if you want, I can put that condition also in 1. I can simply say X belong to B. That's a standard thing. Usually X belong to B. Whenever E belong to B, its complement also belongs to B, and whenever E n or B for all n, then union belongs to B. Okay, now the simplest example, okay, I can see the simplest example, but the most natural example for us, set of measurable subsets of P.R.P. Okay, that is a class of measurable sets. Okay, then we know R or empty set belong to B. Whenever E is measurable, E complement is measurable. Whenever En is measurable for all n, the union also, countable union is also measurable. Therefore, this is the first non-example. Okay, of course, there is a very easy second example. Okay, take B to be P of R itself. Okay, sorry, P of X itself. Okay, so that is obviously a sigma algebra. The third thing is this: if X is any set, okay, look at this E. Okay, so that E or E complement is countable. So this, do you remember, if you have gone through topology, there is no something called co-countable topology. It's something similar. There you will simply say E complement must be countable. But remember, by second condition, its complement should also be there. That means E or E complement must be countable. It's a very natural thing. Okay, please check this is a sigma algebra. Okay, this is an easy exercise. Okay, okay. But the very interesting thing is, you must all learn that, if HI is a family of subgroups, then intersection HI is a subgroup. And similarly, if I alpha is a family of ideals, then intersection I alpha is an ideal. in the ring theory. This is a group theory. This is a ring theory. And in linear algebra, if Wi is family of vector subspaces, then intersection Wi is a vector subspace. This is a linear algebra. And if you know module theory, something similar. And topology also you've seen, if tau alpha is a topology on a set X for each alpha in some indexing set I, then tau equal to intersection tau alpha is also a topology on X. Okay. So now can you guess what I want to say? Yes. If Bi is a sigma algebra on X, then B, which is intersection of Bi, is a sigma algebra on X. Okay. Again, the proof is extremely easy. Yeah. Let's look at X. X belongs to each and every Bi, therefore it belongs to B, right? And if E belongs to B, that means E belongs to Bi for every I, and that means E complement belongs to Bi for each I, that means E complement belongs to intersection Bi, which is B. Okay. All right. And similarly, countable union. If Ens are in B, that means for every N, En belongs to Bi for every I. That means, okay, En belongs to intersection Bi. That is just B. All right. Sorry, let me slightly modify. En belongs to B. This implies En belongs to Bi, fix I. Okay, fix I. Then for all n, En belong to this. Since Bi is a sigma algebra, union En belong to Bi. This is true for all I. Therefore, union En belong to intersection Bi. Okay. Therefore, condition 3 is also true. So, pause, review, proceed. Okay. This I would have left as an exercise, but you could see the third one, I have to be a little alert. Okay. I'm sure you would have got it properly. Right. Now, what is the advantage of this? Whenever intersection of objects or again an object of the same kind, that is, you have a structure, you have a collection of objects, there is a structure on each and every object, like a subgroup structure, ideal structure, vector subspace structure, a topology, or a sigma algebra. What you know is their intersection also has a exactly similar structure. What is the important thing once I have such a thing? This is how one has to learn mathematics as a whole, not as a single subject wise. So I can, if A is a class of subsets of power set X, this is any okay, family of subsets. X. Then I can talk about the smallest sigma algebra. Containing this. Why? Why does it exist? That's because, look at that, the power set of X is a sigma algebra which contains A. Therefore, the class of, okay, write this. This is B. B is a sigma algebra and A is contained in B. This class is non-empty because P of X belong to this, right? Therefore, this is a family of sigma algebras on X. This is sigma algebra on X. Therefore, intersection of B, call it, okay, B in this is a sigma algebra. Okay, this is the smallest sigma algebra containing A. It's a sigma algebra, that's clear. It's the smallest because if C is any sigma algebra such that A is contained in this, then A belong to this C belong to this sigma, and therefore it is here. One of the B's will be C, right? Therefore, this intersection, call it sigma A, okay, sigma A will be contained in C also. Therefore, it's the smallest sigma algebra. Those of you who have learned topology from my thing, group theory I have not taught, linear algebra I have taught, you know that this is very, very standard concept. Okay, so pause, review, proceed. This is going to play an important role. Yes, an important example for us is the following. Let us look at R or Rn. Let us look at U to be this set of all open subset. That is the class of all open subsets in R or Rn. Okay, this is your A now, right? Therefore, by the earlier result, what I know is sigma of U. Okay, let sigma U be the smallest sigma algebra containing all open sets. In I will stick to R, but it's the same thing in Rn. Okay, this is called the Borel sigma algebra. Okay. Now notice that all open intervals J, if J is any open interval, then J belongs to M because J is measurable. Is that right? Now, if U is any open subset of R, then U is union of, in fact, countable union of open intervals. Therefore, U also belongs to M. Therefore, what I know is this script U is contained in script M. This is all open sets. This is all measurable sets. Right? But I know this is a sigma algebra. And what is sigma U? That is the smallest sigma algebra which contains U. But this M already contains U. Therefore, sigma U must be contained in M. So, as a corollary, the Borel sigma algebra, B of R, this is Borel sigma algebra, this is Borel. On R, right, is contained in class of all measurable set. Any element of this is called a Borel set. Okay. Elements of this Borel sigma algebra are called Borel sets. Therefore, any Borel set is measurable. So, pause, review, proceed. You see that? Very simple. Okay, what is sigma algebra? Very simple. The full set must be there, and whenever E is there, its complement must be there. If I take any countable collection of elements from the sigma algebra, its union is also in the sigma algebra. That's it. Okay. The important thing which it did is intersection of sigma algebras is a sigma algebra, and hence there exists a notion of Borel sigma algebra, which is the smallest sigma algebra which contains all open subsets of R or Rn, or if you want need topological space also. Okay, we have found that, right? So we are now ready to give another definition. Okay. So if B is a sigma algebra on X, then the ordered pair XB is a measurable space. Measurable space. See, measurable, that is you can measure, but there is no measure yet. You understand that? The setting is correct. Okay, right? It's eligible candidate kind of thing. Okay, right? So it's a measurable. That is every set. Okay, this is a notion. Okay, this is a definition. So what is a measurable space? It's a set X and a sigma algebra on that. Okay, and if we start with E in anything this, then E is called a measurable set. But usually, if you want to be very technical, B measurable set, because it is measurable only given this B, because it may be in something. Okay, there may be another sigma algebra on X. Okay, it may not be measurable there, so one has to be careful about that. Okay, for example, let's look at only this and X. Okay, this will be a sigma algebra, totally useless sigma algebra, right? And so if I take any proper subset, assume that there is a proper subset, then this will be not measurable. That simply means A is not in B. That's it. Okay, right? So each element of this is called a measurable set. Okay, make sure. Okay, for okay, right. For example, let us look at some set. For example, let us look at x equal to r. Right? We define a sigma algebra where E or E complement is countable. Right? So if I start with an interval 0, 1, that is my E, then E complement is minus infinity to 1 union, 0, 1 to infinity. Okay? Neither you can see E is not countable, E complement is not countable, therefore E is not measurable with respect to this B. Do you understand that? Then E is not B measurable. Okay, but it is E is in M. With respect to this sigma algebra, it is measurable, but with respect to this sigma algebra, namely this B is not Borel. Okay, with respect to this measure, it's not measurable. Do you understand this? Don't get confused. All are very easy concepts. Try to understand. That's enough. There is no need for you to remember any of those things. Concepts are more important. If you understand the concepts, you can always work out these things much more easily. Okay, good. Now it's time for us to define a measure. Measure on a measurable space. It is only measurable, but what is meant by measurable space? It's a set X and a sigma algebra. Okay, is a function mu from B to extended reals, positive reals, 0 to infinity. With what are the properties? The properties are very simple. Mu of the empty set must be 0. And 2, if En is a pairwise disjoint countable collection, of B measurable, I will simply say sets are countable collection in B, then mu of union En. Notice that this is a countable collection, therefore En union also is in B. Right? Therefore mu of E makes sense because the domain of mu is B. Okay, this is summation mu of En. That is, it is countably additive. The function mu is countably additive. Then we call a measure is a measure. That's it. You see that? So I have X. These are my kind of good subsets. Okay, whatever is encoded, you think of this as a good. Okay, these are my good subsets. These are all my elements of B, and mu is countably additive on such sets. Okay, so learn the definition. what is the obvious example? Okay, we are going to deal with, this is a very crucial concept. We are going to deal with only 4 measures, which we will use 4 measures, measurable space and 4 measures. Okay, the first one obviously is R with, that is R with the Lebesgue measurable sets, and my mu equal to the Lebesgue measure. I would already prove it is countably additive, right? It satisfies mu of empty, m of empty set is 0, m of union en equal to summation m of en if ens are pairwise disjoint. We have proved that. That is the first example. So example 1, x equal to r and b equal to m. That is the ordered pair Rm. And my mu equal to m, the Lebesgue measure. See, whatever you have done so far is captured in this particular example. Okay, right. Yeah, there is one more definition I could have called. So if I have a measurable space xb and a measure mu on that, this ordered triple is called a measure space. See, technically it should be measured space because each and every set I have associated the notion of measure, but it's called a measure space. So what is a measure space? It's a measurable space on which a measure is given. Okay, this is the ordered triple. Okay, therefore this is R m, little m is a measure space. This is a, okay. And the second example is cheating. Okay, what is that? My x is still R, but my b, can you guess what it is? B of r, the Borel sigma algebra. Now what is my mu? Mu is m restricted to b. Notice that we know that b is contained in m, and my little m, the Lebesgue measure is defined on capital M. Let me restrict it to b. Okay, then it mu this, okay, R b m is the Borel measure space on R. That is the only thing is exactly the similar thing like earlier, except the sigma algebra of measurable sets is replaced by sigma algebra of Borel sets. Okay, this is, as I said, this is a cheating example, but it's important to understand because when you learn a lot of higher analysis, you will see there are places where you have to, subtle points where you have to distinguish between Lebesgue measure and Borel measurable sets. Okay, but don't worry, but it's a good example, trust me. Okay, sometimes one has to trust. Okay, right. Now example 3 is what we call counting measure. I can do it on any set. Okay, so let x be a set and my b to be power set of x, and mu of v equal to number of elements in E. Therefore, if E is empty, mu of E is 0, and if E is infinite, then mu of E is infinity by definition. Okay, extended real number. If it is a finite set, number of elements in E, in case E is finite. Otherwise, it is infinity. Okay. Again, please check. It is countability additive. Okay. So you have to check mu is countably additive. Okay, this is a good exercise. Okay, many people will take it for granted, but it's a good exercise. Suppose I have En is a collection, pairwise disjoint collection family. Okay, of subsets of X, right? Then if one En is infinite, then union En is infinite. Therefore, mu of union En is infinity, and summation mu of En, okay, one of them is infinite, all of them are non-negative, therefore it is also infinite, therefore equality holds, right? So the only thing is if Ens are finite, every En is finite. Okay, now do you see something interesting? Yeah. So if all my Ens, okay, are pairwise disjoint as I given, right? And suppose they are all non-empty, then this will be infinite. And summation mu of any En also, okay? At least each one of them has one, therefore this will also be infinite. Do you understand what I mean? Okay. Therefore the other thing is there is an N so that Ek is empty for all k greater than equal to N plus 1. Okay. Then you can see. Okay. I leave the details, but just to discuss with your friends, don't assume this. It's very easy to believe, but you should also know how to write a rigorous proof for that. Okay. All right. But more interesting thing is when I take x equal to n, natural number, and let me define, suppose mu of n, that is singleton, is some Pn. Pn is a positive number, right? You understand that? Yeah. Then this mu defines, therefore what is mu of, suppose my E equal to n1 to nk, then what will be mu of E? Mu of E will be, I want it to be countable additive, and therefore I should be mu of n1 plus mu of singleton nk, that is equal to pn1 plus pnk. Now if I write n as union of singleton n, then what will be mu of n? Mu of n will be summation pn n equal to 1 to infinity, right? So notice that these are all non-negative, therefore p, okay, if this is a convergent series, then I'll have a finite measure. Mu of n will be finite. You understand this? For example, my Pn, the simplest thing may be 2 to the power minus n. Right? So, you know how to do that. Okay? So, this is, the first one is called counting measure. This one is called counting measure with weights. Or that is each n singleton. Earlier I counted as 1. It gave uniform weight, whereas now it's not uniform weight. The weight is Pn. Okay? This Pn stands for probability. If you have some idea about probability, that means, okay, the singleton, the even singleton n, okay, its a probability is P. Okay, if you don't understand, forget it. This is good enough for us. The last example which I want to talk about, it is a very interesting example. So this is 1, okay, this is 2, this is 3, okay, this is example 4 and example 5. I said 4 examples, but mentally I counted 3 and 4 as 1. So example 5 is the so-called Dirac measure. Let x be any set, okay, fix a point x naught in x, and my b to be the power set of x. Okay, then define mu of e to be 1 if x naught is in e, otherwise 0. Okay, that's it. So this is a Dirac measure, okay, based at or at x naught. Okay, it's something like if you have learned topology from me, it's something like a VIP topology. So you take any set E, it is of some value if only if x naught is there. Otherwise it is 0. Yeah, attend a call. Okay, so this is my x naught is, so I have, this is my x. Okay, now start with anything E. Okay, my x naught is this fellow. If x naught is here, oh, I wanted this fellow. Oh, yeah, if x naught is here, this is my x naught. And if we take some other a, okay, then this measure is 0 and this measure is 1. It does not matter how big or how small it is. Think of x equal to r and my x naught equal to 0, right? That's it. For example, the set of irrationals will be of measure 0. Singleton 0 will be of measure 1. Or the unit interval 0, 1 will be measure 1. Or this interval 0 to 7 will be measure 1. Whereas minus 20,000, 2000, 20 to 10,000 to minus 1, this will be a measure 0. Now have an idea, that's it. Okay, these are the most basic examples. Okay, now so we want to look at some important properties. With that I will stop. So let x be mu be a measure space. I want to look at the properties of mu. The first thing is mu is finitely additive. You may think these are almost obvious, but you will see the subtle assumption is very much needed. Suppose I have E1 to UK is a pairwise En is a pairwise disjoint family. Okay, my EKs are in N. Right? Now I can define EK to be empty set if K is greater than N. Now let's look at EK. Now K running over all of N. This is a pairwise disjoint family. Family from B. Elements from B, right? Therefore, by countable additivity, mu of union EK, K equal to 1 to infinity, equal to summation mu of EK. This is by countable additivity. This is the assumption 2. This is the second property of measure, right? Now what is, since first property says mu of empty set is 0, therefore this is mu of right hand side, mu of E1 plus mu of En. I don't know what they are, but after that everything is 0 plus 0 plus 0. Therefore this is nothing other than mu of E1 plus mu of En. Okay, because all the partial sums after this, for any m greater than or equal to n, the partial sum is nothing other than Sn, which is mu of E1 plus mu of En. Therefore this series is convergent and it converges to this finite sum of the finite numbers. Is that clear to you? Not finite numbers, what I mean is finite sum. Is that clear? Okay, but let's look at this one. What is Ek? K equal to 1 to infinity. This is nothing other than again Ek K equal to 1 to n, because for K greater than to n, Ek is empty, right? Therefore what you have is mu of 1 to n of Ek equals summation mu of Ek k equal to 1 to n. This is finite additivity. Okay. So pause, review, proceed. Second property is the monotonicity. See, this is something very interesting because many times people take it for granted. Remember, in the case of Lebesgue measure, we proved finite additivity first and we knew countable additivity. Put both together, we proved it's countably additive. See, appreciate the way mathematics develops. In the case of Lebesgue measure theory, I first proved the Lebesgue measure is finitely additive. Then we already know Lebesgue measure is nothing other than outer measure restriction and therefore it is countably subadditive. Both these things, okay, gave rise to countable additivity of the Lebesgue measure. But here, countable additivity was given to us. We want to prove finite additivity. For that, we needed the first assumption. This is something very, see, people do not understand some of the properties very well. Okay, they somewhat think it's obvious, take it for granted, don't. For example, similar thing in the case of definition of linear algebra vector space, you would have seen. Okay, one dot the vector x is x all for all x in the vector space. Okay, this is very important. Okay, you may take it, you think of it as numbers, one dot any number is again the same number, you take it for granted. It's very important because if I had two vectors, suppose I have x, the vector x, then x plus x makes sense. This is a vector. And 2 dot x also makes sense because 2 is a scalar. This is a vector, right? 2 dot x also makes sense. But you will immediately think x plus x is 2x. When you say that, what you mean by that is this vector scalar multiplied by 2. Why are they equal? That is because of this. See, appreciate mathematics. If you understand better, then you will see things become much easier. Okay. So pause, review, proceed. Now the second thing is monotonicity. What is it? If A and B are in script B, measurable, and if A is contained in B, then mu of A is less than or equal to mu of B. This again is easy because remember, B I can write as A union B minus A. Now notice that B minus A is B intersection A complement, therefore this is in B. Since A is in B, A complement is in B, the intersection is also in complement because I should have said that countable union, right? Therefore finite union is also there, finite intersection will also be there, exactly the same logic. Okay, therefore this is also, therefore, okay, now this is a disjoint union. Therefore by finite additivity, that is by 1, okay, implies mu of B equal to mu of A plus now notice that this is non-negative. Therefore mu of B is greater than or equal to mu of B. So this is what we prove. Okay, something which I said there, let me try to explain. We know that union, if ENs are there and union EN is there. I said this is a countable family. Okay, therefore the countable family, remember, may also include finite family. Therefore finite thing. The next thing is, therefore if A and B are in B, then I know A union B is in B and A complement union B complement is in B, right? But this is nothing other than A intersection B complement, that is in B, but that implies A intersection B is in B. Okay, exactly the way we proved earlier. Okay, therefore this may, see, the whole thing is to show that this belongs to B. That's why I wanted to do that. Okay, the last one is countable subadditivity of a measure. What does it mean? Suppose ENs are in be for all n, but they need not be pairwise disjoint. But what we want to say is mu of union n equal to 1 to infinity, is less than or equal to mu of en. Okay, this is what we want to prove. But this proof is again easy. We have seen arguments earlier. Let a1 equal to e1, a2 equal to e2 minus e1, a3 equal to e3 minus e1 union e2, etc. In general, an equal to en minus k equal to 1 to n minus 1 ek. Right? Notice that each ak is measurable. Yeah, that's a logic we had already done earlier. Right? Therefore, each ak. And the next thing is union an is same as union en. This we have proved. Okay, in the Lebesgue measurable sets, set theoretical thing, this we have proved. Okay, again go through the proof. Or check again. Right, okay. Therefore, we know that mu of union an, this is a pairwise disjoint. Okay, this collection an is pairwise disjoint. This also seen earlier. This is set theory. Therefore, this by countable additivity, this is going to mu of an. This is countable additivity. But remember, by monotonicity, each an is contained in en, therefore by monotonicity, mu of an is contained less than or equal to mu of en for all n. Therefore, this is less than or equal to mu of en. But this is equal to mu of union en. So we proved the result. So all are easy. Some of the arguments are very similar to what we have done, but do not skip. Okay, enjoy, go through it. Okay, if you are not sure, go back to Lebesgue measure, that video, check it, again come back. Okay, once you, some of the thing may be look obvious, you want to believe, please don't. Go through the proof, rigorous proof. Okay, so that you will be very, very confident of what you are talking about in future. Yeah, I hope you enjoyed this lecture, and if I don't think I have forgotten anything, so next session should be on measurable functions. I hope I don't think that I have forgotten something. Okay, stay safe. We will meet again.